Hello students, today we are going to learn some important concept in metrics. You know that matrices are very important in physics, especially when you want to solve problems in classical mechanics or electromagnetism or in optics or especially in quantum mechanics. We many times use matrices to solve equations. So this is a very convenient way to address many of the physical problems. So this topic is very important for physics as well, though it is a topic in mathematics. So today we are going to understand about eigenvalues and eigenvectors of matrices. Suppose I have a vector, say x, and we know that any vector can be written in terms of its coordinates as, let me say, I write this as 5i plus 2j plus say 10k. Okay, now this vector can be represented in form of a matrix as like this way, as 5, a 2, a 10, which is a column matrix x. So the vector x can be represented in the form of a matrix as 5, 2, 10 column matrix. Now suppose I have a matrix or an operator. I say that operator is basically a matrix, but say I have an operator, say x, which is again a matrix. And this operator, when multiplied by x, or we say that when operator operates on x, we get again x, but that x is multiplied by a scalar, say lambda. So operator operating on x is giving lambda into x, where lambda is a scalar, okay, or it is a constant. So if I get in this way, in this form, you can say that this lambda as the eigenvalue of the vector x. Okay, if I have an operator a which is operating on x, and this result gives x multiplied by a lambda or lambda multiplied by x, then I can say that this lambda is an eigenvalue. Okay, so now our attempt is to find more about this x. Okay, so that means I have to find the lambda for which we get ax is equal to lambda x. Okay, now lambda is an unknown quantity, a is an operator which is operating on x, which we know. Now suppose I am writing this in the form of an equation. Say I write a minus, I bring this lambda also towards here. A is a matrix, right? So lambda is a constant, so I want to make it as a matrix. So what I do is I can consider this lambda as multiplied by I, where I is an identity matrix. Okay, that is, I can write this as a minus lambda into I. Okay, and this is x equal to 0. That is no problem. That is where this I is basically a identity matrix, where if it is a 2 by 2 matrix, I can say I as, if A is a 2 by 2 matrix, I can write I as 0, 1. Or if A is a 3 by 3 matrix, I can write it as 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. So lambda I is such a unit matrix. Now let me, okay, so a minus lambda I into x is equal to 0. If I write this as an equation. Now let me consider this a minus lambda I as a minus lambda I. Let me call it as k. Okay, so if it is k, I can write k into x is equal to 0. Right? Now what is the solution of this x for this? I can say that if suppose this K, we know that K is a matrix, right? Because A is a matrix, lambda multiplied by I is a matrix, so resultant K is a resultant matrix. Suppose this matrix has an inverse. Let me say that if K inverse exists. If K inverse exists, what does that mean? Or I can write, if K inverse exists, I can multiply it with the K inverse on both sides of this equation. So I can write it as K inverse, okay, Kx is equal to K inverse of null matrix, and that is again 0. Okay, and what is this K inverse into K? If I have an inverse of a matrix, then that matrix inverse multiplied by K is actually I. Okay, identity matrix. So then I can write it as I into X, or I can simply write X equal to 0. So what does that mean? Here X is equal to 0 means this is a trivial solution. Trivial solution means 0 is the solution of this. That's very simple and is a solution which we are not much bothered about. So this is a trivial solution. And now suppose this is possible only if K inverse exists. Now suppose if the K inverse doesn't exist. The K inverse does not exist. What happens? We know that K inverse doesn't exist, which means that the determinant K is not equal to 0. That is, if K inverse exists, we know that K inverse is adjoint A or adjoint K divided by determinant K. If the K inverse exists, we can say the determinant K cannot be equal to 0. And suppose if K inverse does not exist, we can say that the determinant K is equal to 0. So in that case, okay, if determinant K is equal to 0, then we can say that the K inverse does not exist. If that is the case, then we can say that K inverse cannot exist. Okay, so this solution cannot exist. We can say that then the X will have some other solution. That is K inverse. If K inverse does not exist, we can say that the K cannot be equal to, or X cannot be equal to 0. So that means X will have value other than 0. Okay, did you understand? That is, if K inverse exists, I can say that X is equal to 0. Then I can say that it has trivial solution. And suppose this K inverse does not exist, or the whole process is not possible, then I can say that X will have a solution other than 0, or non-trivial solution exists. Okay, so then we can say that if determinant K is equal to 0, or if the K inverse does not exist, I can say X will have some non-trivial solution. Okay, so now I can say that a minus, and I write that a x is equal to lambda x. Okay, then for this particular value of lambda, we get non-zero solution for x. If this is the case, if K inverse does not exist, I can say that when a is equal to lambda x, when we write, then x will have some non-trivial solution. Okay, now the value of the lambda for which we get non-zero solution of x. If we have a value of the lambda for which we have non-trivial solution for x, that is if we have solution other than 0, then I can say that lambda is the eigenvalue of the matrix A. Okay, what I said is, when we write an equation like this, or I can say that if I have a vector say x, and when an operator A, or if a matrix operates on the x and I get the solution as lambda into x, then if x has a solution, non-zero solution or a non-trivial solution, then if such a non-trivial solution, and if such an equation exists, or if such a equation is satisfied, then the value of the lambda for which this equation is satisfied, we can call that lambda as the eigenvalue of the matrix. Eigenvalue of the matrix A. Okay, now for different eigenvalues of the matrix lambda, the X can have different solutions. So those vectors for a particular value of say lambda 1, I will have a matrix say X or vector say x1 which has the solution as x1, y1, z1. Then I can call that vector corresponding to that eigenvalue lambda 1 as the eigenvector corresponding to the eigenvalue lambda 1. Now this lambda can have different value also. Say so lambda for such a solution to exist, lambda 1 need not have only a single value. Lambda eigenvalues can be different. Suppose I have another eigenvalue lambda 2 corresponding satisfying this equation. So then there can have, so I have a lambda, I have a solution for eigenvalue as lambda 2. Then correspondingly there can be another vector, okay, which is satisfying the condition, so sorry, y2 z2, which is satisfying the condition ax is equal to lambda 2 into x. Then that value of x corresponding to this lambda eigenvalue lambda 2 is the eigenvector corresponding to eigenvalue lambda 2. So this is about the eigenvalues and eigenvectors of a matrix. So I hope you understood, and one of our major tasks for solving is or doing matrices, when we do matrices, our major task is to find, so we will be given a matrix A, okay, then our task will be to find the eigenvalues corresponding to this matrix A, or to find the eigenvectors corresponding to the matrix A. So this is one of the important problems addressed in matrices. So this will be our one of the important theme which we are going to discuss. So in the coming video, we will be discussing one important problem from the matrix where we have to find the eigenvalue and eigenvectors of a given matrix. Okay, thank you. I hope you understood.